Before we move on to the other questions we had, let's look at a quick application of coloring and colorability. So the application is a problem of scheduling or placement. So the problem you would typically have that you want to solve is that you have a number of meetings or events or whatever uh, involving many people. Some of them can be at the same time, but some not, because maybe you're scheduling classes and the same students take multiple classes. So you have to figure out how to compress your schedule as much as possible without any two conflicting items being scheduled at the same time. Or you need to place a number of items that have to be placed separately from each other, some of them, so you can't just put them all in one place, and you have to figure out the optimal strategy. An example of the latter is that you have 4 chemicals, A, B, C, and D, and you want to put them in as few containers as possible, but some of them react with each other, so they definitely need to be in separate containers. So for example, this graph means that B reacts with A, C reacts with B and A, and so on. So the mathematical way to model this, or a mathematical way to model this, is you draw a graph with your vertices corresponding to the chemicals or events you want to schedule or whatever. And in your graph, 2 vertices are adjacent if and only if they cannot coexist. So they react, or in this case, with chemicals. So let's do this. So we have our A, B, C, and D. A reacts with B, A reacts with C. Obviously, this scheme is symmetric. B and C react with each other, and D only reacts with B. And then, what do we want to do? We want to place them in containers so that no two chemicals that react are placed in the same container. This sounds just as a rephrasing of the saying that we want to color them in colors so that no two adjacent vertices have the same color. So that's precisely what we need. And in this case, how many colors do we need? So this is a complete graph on 3 vertices. So we're going to need 3 colors. And the only thing we need to make sure with D is that it's not in the same color/container as B. So it can be either blue or red. So we can color it, for example, red. And in this case, we are going to need 3 containers. So coloring graphs might be used to represent such problems. And this is quite handy when you have more than 4 chemicals. So then it's convenient to have the machinery of graph theory that will help you. For example, if you know that the graph you get is planar, even if you have thousands of chemicals, you know that 6 containers will be enough. Actually 5, and by the 4-color theorem, 4. So it's quite nifty.